Hello everyone, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. Hope that our earlier videos have been informative and useful to you all. This video on capacitance is packed with certain basic information on capacitance of a conductor, energy stored in a conductor, principle of capacitor, capacitance of parallel plate capacitors, dielectric and polarization, behavior of a dielectric in electric field, series and parallel combination of capacitors, and loss of energy during redistribution of charges. It also has some easy methods to solve difficult problems in capacitances. So let us begin with capacitance of a conductor. Here capacitance of a conductor is defined as the measure of ability to store charge. If we give charge Q to a conductor, then its potential increases. The charge given to a conductor is directly proportional to its potential raised. Charge Q proportional to potential V. To remove the proportionality sign, we introduce a constant C. C is known as the constant of proportionality and is called capacity or capacitance of a conductor. The capacitance C here is equal to the ratio Q upon V and is called as equation number 1. The capacitance is equal to the ratio of charge on it to its potential. The capacitance of a conductor depends on shape and size of the conductor, nature of medium surrounding the conductor, and the presence of nearby conductor. So what does capacitance of a single conductor system depend on? Shape and size of the conductor. Secondly, nature of medium surrounding the conductor. For a system of two conductors, it is the presence of nearby conductor which would affect the capacitance. If V equals 1 volt, then from equation 1, C would be equal to Q. So what is capacitance? Capacitance of conductor is numerically equal to the charge that would be required to raise its potential by 1 volt. The SI unit of capacitance is farad, while the CGS unit is stat farad. So farad is supposed to be the unit of capacitance in SI system and stat farad in the CGS system. What is 1 farad equal to? It is equal to the ratio of 1 coulomb to 1 volt. So capacitance of a conductor is said to be 1 farad if a charge of 1 coulomb is required to raise its potential by 1 volt. What are the dimensions of capacitance? Ratio C can be defined as Q upon V. V is W upon Q. The dimensions of charge are A1 T power 1 and dimensions of the work done are M1 L2 T power minus 2. So what are the dimensions of capacitance? M minus 1, L power minus 2, T power 4 and ampere power 2. Now the question is, what are the factors on which capacitance of a conductor does not depend upon? It does not depend upon charge given and the potential raised for a single conductor system. Because if we double the charge, then the potential is also doubled and the ratio remains unchanged. Similarly, it does not depend upon nature of material of the conductor and thickness of conductor. Capacitance of an isolated sphere. So here we take a spherical conductor of radius r. We give it a total charge Q to raise the potential to a maximum of V volts. So this represents a sphere with radius r and a charge given Q to raise the potential to V. This maximum potential on the surface is 1 upon 4 pi epsilon 0 Q upon R. What is the definition of capacitance? C will be equal to Q upon V and this ratio would be 4 pi epsilon 0 R. So what does capacitance depends on? Nature of medium and size of the sphere through radius. So C is given by 4 pi epsilon 0 R. Here let us calculate what would be the capacitance of Earth. Earth can also be treated as a sphere of radius 6400 kilometer. So C would be equal to 4 pi epsilon 0 R and 4 pi epsilon 0 is 1 upon 9 into 10 raised to power 9 and radius is 6.4 into 10 raised to power 6 meter. And the calculation gives the capacitance of Earth as 711 microfarad. Now we need to calculate what is the energy stored in a conductor. Now, how do we charge a conductor? The amount of work done in charging the conductor is stored as potential energy of conductor. The process of charging involves transfer of charge from infinity to that conductor. Now, work done in bringing the first charge Q would be 0. And what would be the work done in increasing the charge from Q to Q plus dQ? This work done would be equal to V times dQ. What is V? The potential produced by the initial charge Q, and then V can be written as Q upon C. So dW is equal to Q upon C dQ. The total work done in increasing the charge from 0 to Q, W would be equal to 0 say Q dW. It is 1 upon C Q dQ, the limits ranging from 0 to a maximum charge Q. And the integration on solution gives Q square upon 2C. This work done is stored as change in potential energy of the conductor. So potential energy, that is energy stored, would be Q square upon 2C. Replace Q is equal to CV, which gives me half QV, and also another time replace second Q by CV, it will give me half CV square. So we have three relations here. One, Q square upon 2C, half QV and half CV square. Now we want to understand what is the principle of capacitor. Then we'll define what is a capacitor. The capacitance of an insulated charged conductor is increased appreciably by bringing near it an earthed connected uncharged conductor. So what does it say? If I want to increase the capacitance of an insulated charged conductor, then bring near and grounded connected uncharged conductor near it. How does it leads to the increase of capacitance? Let us see. We have two conductors A and B. So we say, let us take an insulated metallic plate A. It is the charged positively to a potential V by giving it a charge Q. So we have a metal plate A. It is charged and charged to a potential V by giving it a charge capital Q. When an uncharged identical metallic plate B is brought near to it, then by induction a negative charge Q is induced on the inner surface of B and a positive charge plus Q is induced on the outer side of the conductor B. The negative charge would try to reduce the potential of conductor A, while the positive charge would tend to increase the potential of plate A. As the negative charge is closer than the positive charge, so potential of A is slightly reduced. To raise the potential back to its original value, additional charge is given to plate A, and that means the ability to store charge has increased, which will lead to increase of capacitance of the conductor A. So pictorially I can say this represents conductor A with a positive charge. Here we have minus Q charge on the inner surface and positive charge on the outer surface. Now what we do is we ground the outer surface. On grounding, what will happen? The electrons from the ground come and neutralize the positive charge here. So it works as the free charge and is neutralized. The inner negative charge is a bound charge under the influence of attractive force of the positive charge. So what do we find? When the outer surface of the plate B is grounded, then positive charge on the outer surface of the B being free flows to the ground. The negative charge on the inner surface of B cannot flow as it is a bound charge. The potential of the plate A is reduced because of induced negative charge on the inner side of the plate B. The decrease of potential of the plate A leads to the increase in capacitance because Q is inversely proportional to V. Sorry, C is inversely proportional to V. So more charge can be given to conductor A without increasing the potential difference between the plates A and B. Now question is, what is capacitor? A system of two conductors carrying equal and opposite charge separated by a dielectric medium makes a capacitor. So we have two plates here. One plate carries a positive charge, another carries a negative charge, and now you separate it with the dielectric medium. This system would be then called as a capacitor. Q is the charge on each plate of the capacitor. It is the charge on each plate, and the total charge on the capacitor is 0 because one of the plate carries positive Q charge, another plate carries minus Q charge, so the entire system carries a charge which would be 0. Now we need to calculate what would be the capacitance of a parallel plate capacitor. A parallel plate capacitor consists of two large plane and parallel conducting plates separated by a small distance with air as the medium. Here Q would be the charge on each plate of the capacitor, A is the area of cross section of each plate, charge density for each plate is sigma, and D is the distance of separation between the plates. So we have a plate here with positive charge, a plate with negative charge, and the direction of the electric field here. D is the distance of separation. This represents the charge density, that is charge per unit area. Here the distance of separation D is very much smaller than the linear dimensions of the plate, that is D square is very much less than A. The electric field between the plates would be given by sigma upon epsilon 0. Sigma is charge per unit area. The direction of the electric field is from positive to negative plate. The field is localized between the two plates and is uniform. The fields with the finite area cannot have a uniform field because at the edges of the plates the field lines bend outwards at the edges, and this is basically called as fringing of the field. For D square less than A, these effects are ignored. That means the fringing effect is small or negligible because D square is very much less than A. That is why we are making use of this approximation. The potential difference between the plates is given by the product of electric field and the distance of separation. So I get electric field as Q upon epsilon 0 A multiplied by D. The capacitance C is defined as the ratio Q upon V, which gives me epsilon 0 A upon D. So what does the capacitance of a parallel plate capacitor depend on? Nature of medium, shape and size of the plate, distance of separation. Right? So these are the three factors upon which the capacity of a parallel plate capacitor depends upon. If I take A is equal to 1 meter square and D is 1 millimeter, then the capacitance would be equal to 8.85 into 10 raised to the power minus 9 farad. A relatively larger unit of capacitance is farad. So to have a feel of largeness, let us calculate what would be the area of the plates required to have a capacitor of 1 farad capacitance for a separation of 1 centimeter. So A would be CD upon epsilon 0. C is 1 farad, distance is 1 centimeter, and epsilon 0 1 upon is 8.85 into 10 raised to the power minus 12 SI units. So it gives me 10 raised to the power 9 meter square. What does this show? It shows that we require a plate area of 30 kilometer in length and breadth to generate a capacitor of 1 farad capacity with air as the medium. So you can imagine such a capacitor is practically not possible. Now let us see and understand the concept of dielectrics and polarization. What are dielectrics? Dielectrics are basically non-conducting materials which have either 0 or negligible number of free electrons. So we have either 0 or negligible number of free electrons. Now there are two types of dielectrics, non-polar dielectric and polar dielectric. Let us first take up is non-polar dielectric. The molecules in which the center of negative and the positive charge coincide with each other due to symmetry are called non-polar dielectrics, like oxygen and hydrogen molecules. They do not have a permanent or an intrinsic dipole moment. In absence of electric field, no dipoles are found to exist. So in non-polar system, they do not have dipole moment and neither dipoles are found to exist in absence of electric field. What will happen in the presence of electric field? In presence of electric field, the positive and the negative charges of the non-polar molecules are displaced in opposite directions. This displacement stops when the external force is balanced by the restoring force produced due to internal fields in the molecule. The non-polar molecule thus develops an induced dipole moment. The dielectric is now said to be polarized by the external field. The induced dipole moment is proportional to the field strength. The induced dipole moment is in the direction of external electric field. The induced dipole moment for different molecules add to produce a net dipole moment in the direction of electric field. So in absence of electric field, the center of positive and negative charges are coinciding with each other. No dipole formation takes place. While in presence of external electric field, what is happening? The center of negative and positive charges have been slightly displaced, producing induced dipole. In presence of field, the induced dipoles are trying themselves to align in the direction of external field to produce a small dipole moment. Now the second type of material that we talk about is non-polar dielectric. Here the molecules in which the center of positive and the negative charges are separated even in the absence of electric field are called polar molecules like HCl and H2O. Here the center of positive and negative charges remain separated due to asymmetric shape of molecules. Polar molecules have a permanent dipole moment. In absence of any external field, the different dipole moments are randomly oriented due to thermal agitation, and therefore the net dipole moment is a 0. The sum of n random vectors is 0, and that is why the net dipole moment also comes out to be 0 in absence of electric field. In presence of electric field, the dipole would experience a torque and will try to align in the direction of field. A net dipole moment in the direction of external field is produced, thus the dielectric is said to be polarized. This concept is represented pictorially in these two figures. So in case of polar or non-polar dielectrics, they develop a net dipole moment in the presence of external field. This process of alignment of permanent or induced dipoles in the direction of applied field is called polarization. Now the question is, how do we measure polarization numerically? So polarization is numerically equal to the dipole moment acquired per unit volume. It provides us a measure of the extent of polarization. That means how much polarization has taken place. So polarization defined by dipole moment acquired upon volume of a dielectric. Here P is the dipole moment of each atom. N represents number density of dipoles. So it represents number of dipoles per unit volume. So polarization P would be equal to N times the dipole moment. N means number of dipoles per unit volume, and dipole moment is Qi times T, and volume given by A into D. D cancels out. So charge per unit area is induced surface charge density. When the polarization is normal to the surface, then numerically the polarization would be equal to surface charge density of induced charges. Now, in dielectrics, the polarization P is proportional to the electric field. More is the strength of the electric field, more would be the extent of polarization. So P would be equal to epsilon 0 chi E times E. Here epsilon 0 has just been induced or has been introduced to make chi E dimensionless. Chi is nothing but a constant and is known as electric susceptibility of dielectric medium. Chi E is supposed to be dimensionless. Susceptibility. What is the physical significance? It provides me a measure of ability of ease of polarization in the direction of electric field. कोई मटेरियल कितनी आसानी से इलेक्ट्रिक फील्ड में रखने पर पोलराइज हो जाता है, उसको अगर मेजर करना है तो दैट वुड बी मेजर्ड इन टर्म्स ऑफ ससेप्टेबिलिटी. The susceptibility of vacuum is supposed to be 0. Why? Because in vacuum there are no molecules whose charges can be displaced by the electric field. and that is why in vacuum the susceptibility comes out to be 0. Now my question is, how will a dielectric behave when kept in an external electric field? So here we have an external electric field is 0 and we have a dielectric placed in the electric field. So we say when a dielectric slab is placed between the plates of a charged capacitor, then induced dipoles are formed. The internal charges of dipoles cancel each other's effect and produce induced charges on the surface of dielectric. The polarized dielectric is equivalent to two charged surfaces with induced surface charge densities plus minus sigma. The field produced by induced surface charges is opposite to the external field. The surface charge density plus minus sigma arises from the bound charges. Now just see here what is being said. In presence of external electric field, then induced dipole formation is taking place. The inner charges, they cancel each other's effect, and only the charges would be present on the surfaces of the dielectric to produce the surface charge densities plus minus sigma I. The field produced by the induced charge is opposite to the external field, right? So what would be the direction of the induced field here? It would be from the positive side to the negative side. The charge density sigma I is arising due to bound charges and is not arising due to free charges. The resultant electric field inside the dielectric slab placed inside the electric field E0 will be equal to E0 minus EI. The electric field due to induced surface charges is given by EI would be equal to sigma upon epsilon 0. Sigma is nothing but P upon epsilon 0, which is epsilon 0 chi times E. Epsilon 0 cancels, it is Xc times E. So E would be equal to E0 minus EI, E0 minus Xc times E, or E0 could be E into 1 plus Xc. So E0 upon E is 1 plus chi E. 1 plus chi is nothing but constant for dielectrics and is called relative permittivity epsilon R, or the dielectric constant. So epsilon R is equal to 1 plus Xe. For vacuum, Xe would be equal to 0, so epsilon R would come out to be 1. Now from the two equations we can say E0 upon E would be equal to epsilon R by K. But K is greater than 1, so E0 would be greater than E. Thus, on introducing a dielectric slab, the electric field is reduced between the plates of a charged capacitor. If V0 is the potential difference between the plates without dielectric and V is the dielectric, V is the potential difference with the dielectric, then V0 upon V would be equal to E0 upon E would be equal to K. Here also K is greater than 1, so V0 is greater than V. So as you insert the dielectric in a charged capacitor, then the potential difference also decreases. Now what happens to capacitance? So C0 would be given by Q0 upon V0 and C would be given by Q0 upon V. So C upon C0 is V0 upon V. So C upon C0 would be epsilon R equals to K. Since K is greater than 1, so C is greater than C0. The introduction of the dielectric increases the capacity of a capacitor. Here we can calculate what would be the magnitude of the induced charges, and we can also calculate what would be the magnitude of the induced surface charge density. Here E would be equal to E0 minus EI, so EI would be E0 minus E. So E can be replaced by E0 by K, so I get E0 into 1 minus 1 upon K. Here EI is sigma I upon epsilon 0 and E0 is sigma by epsilon 0. So substitute here, epsilon cancels to give me sigma I would be sigma into 1 minus 1 upon K. Similarly, charge Qi would be equal to Q into 1 minus 1 upon K. These two equations are helpful in calculating what would be the magnitude of the induced charge and what would be the value of induced charge density. In absence of dielectric, K is equal to epsilon R is equal to 1. So Qi would be equal to 0. For a conducting slab, K would be equal to epsilon R. So 1 upon infinity would be 0, so Qi would be equal to Q. The magnitude of the induced charge would be equal to the charge itself. Now question is, What is dielectric strength? It is the maximum value of electric field that a dielectric can tolerate without electric breakdown, and this would be called as dielectric strength. What is the unit of dielectric strength? It is same as the unit of electric field. If the field exceeds the dielectric strength, then insulating properties break down and the medium begins to conduct. The dielectric strength is different for different materials. A medium with high dielectric strength increases the operating voltage. The dielectric strength for air is 3 into 10 raised to power 6 volt per meter. Now we had a question like, what are the uses of dielectrics? Alright, 3 uses of dielectrics. So what are those? The first one, it says dielectrics, they help to solve the mechanical problem of maintaining two large metallic charged sheets at an extremely small separation. They can tolerate larger electric fields without breakdown. And finally, they increase the capacity of the capacitor, one of the most important applications of dielectrics. Now we come to combination of capacitors. The capacitors can be combined either in series combination or parallel combination. Then let us pick up from series combination. Capacitors are said to be connected in series between 2 points if there is only one path available to move from one point to another. Capacitors are said to be connected in series if the charge on each plate of the capacitor is equal. The potential difference across all capacitors is different, and the sum of the potential difference across all capacitors would be equal to the potential of charging battery. So in series, the charge on each plate of the capacitor would be same, the potential across each capacitor would be different, and the total potentials on the capacitors would be equal to the input potential provided by the charging battery. Now we are having 3 capacitors here connected in series. If a charge plus Q is given to the first plate, it would induce equal and opposite charge on the inner side of the plate. 2. On the outer side, it will have a positive charge. What will happen? The negatively charged electrons from the third plate would come and neutralize this charge. So this plate would be having deficiency of electrons, so would acquire positive charge. The process continues and the alternate plates get positive and negative charges which are equal in magnitude. The potential difference across the plates of the capacitor C1 is V1, across C2 is V2, and across C3 is V3. The total potential applied here in the system is V. So when a charge Q is given to the first plate, then by induction minus Q is developed on the inner plate and plus Q on the outer side of the second plate. The charge on each plate of the capacitor is the same. Since capacitances are different, so potential difference across plates of each capacitors is different. Here V is the applied potential difference, and V1, V2 and V3 are the potential differences across each of the capacitors. Here V1 would be equal to Q of C1, V2 would be Q upon C2, V3 would be Q upon C3. If CS is the equivalent capacitance, then V would be Q upon CS. As per conservation of energy, V would be equal to V1 plus V2 plus V3. So Q upon CS would be Q upon C1 plus Q upon C2 plus Q upon C3. The charge Q cancels on both the sides, giving me 1 upon CS is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. The reciprocal of equivalent capacitance is equal to sum of the reciprocals of equivalent of individual capacitances of individual So in series combination, the equivalent capacitance is smaller than the smallest of the individual capacitance. So the series combination is basically used to decrease the capacitance of the combination. It is normally used where the working voltage is high and single capacitor cannot sustain it. So you apply large number of capacitances in series, divide the voltages to sustain the high voltage. When n identical capacitors are connected in series, then equivalent capacitance is 1 upon Cs is equal to 1 upon C plus 1 upon C n times. That would be equal to n upon C. So Cs would be equal to C by n. Now we pick up is the other type of combination, which is parallel combination. Here the capacitors are said to be connected in parallel if it is possible to move from one point to another along different paths. The potential difference across each capacitor is same and is equal to the applied voltage. The charge across each capacitor is different and is proportional to its capacitance. The total charge would be equal to sum of the charges on the individual capacitors. So in parallel, potential difference across each capacitor is same, but the charges are different. Here Q is the total charge drawn from the source, as different capacitors have different capacitances, so they will draw different charges from the source. So let us say Q1, Q2 and Q3 is the charge on each of the three capacitors. As per law of conservation of charge, Q would be Q1 plus Q2 plus Q3. If Cp is the equivalent capacitance in parallel combination, then Q would be Cp times V. Q1 would be C1V, Q2 would be C2V and Q3 would be C3V. So substituting here, CPV would be equal to C1V plus C2V plus C3V, V cancels, giving me Cp would be equal to C1 plus C2 plus C3. The equivalent capacitance in parallel combination is equal to sum of individual capacitances. The equivalent capacitance is larger than the largest of the individual capacitance. So where is parallel combination used? To increase the capacitance. When n identical capacitors are connected then equivalent capacitance in parallel would be n times C. Now the ratio of equivalent capacitance of n identical capacitors in parallel to series. So Cp is NC and Cs would be C by n. So Cp would be now equal to n square Cs, a useful relation while doing certain numericals. Energy stored in a capacitor. In the first part we calculated what would be the energy stored in a conductor. Now we have energy stored in a capacitor. Now what would the process of charging of a capacitor involve? The process of charging of a capacitor involves the transfer of electrons from one plate to another with the help of an external battery. The work done in transfer of the charge is stored in the form of potential energy, because electrostatic force is a conservative force. The final potential energy is independent of the way in which the charge configuration of capacitor is built up. The potential energy is stored in the electric field between the plates of the capacitor. We first calculate the work done in small step involving transfer of infinitely small amount of charge. Let a small charge be transferred from one plate to another. So work done in the transfer of charge dq would be given by dw equals v times dq. V is q upon c. So total work done in increasing the charge from 0 to q would be again given by integration 0 say q dw 1 upon c integration q dq. Substitute the limits to obtain the relation q square upon 2c. So by definition of potential energy, U would be either equal to q square upon 2c, half qv or half cv square. The relation is exactly identical to a single conductor system. यहाँ पर the only difference is Q represents charge on each plate of the capacitor, C represents the capacity of the capacitor, and V represents the potential difference between the two plates of the capacitor. Now let us see certain important points from these relations. The energy spent by the battery in raising the potential difference of the plate to V volts is Q into V. But the useful energy stored in the capacitor is half QV. So energy lost in the form of heat during the charging of the capacitor is half QV. So what is the efficiency of the charging process? It is simply equal to 50%. Now let us calculate what would be the relation for energy density. First of all, let us define what is energy density. The energy stored per unit volume of space is called energy density. Energy density U would be equal to total energy stored upon volume of capacitor. Total energy stored half CV square and the volume is A upon D. Half capacitance is epsilon 0 A upon D V square upon AD. So half epsilon 0 V upon D ka whole square. That is half epsilon 0 E square. The electric field between the plates is given by sigma upon epsilon 0. So potential energy can be represented as half epsilon 0 E square or sigma square upon 2 epsilon 0. Though this relation is derived for a parallel plate capacitor, but the result of energy density holds for electric field due to any configuration of charges. So relation for energy density is either half epsilon 0 E square or sigma square upon 2 epsilon 0. Now let us calculate what is the force between the plates of a capacitor. There are two plates, one carries positive charge and another carries negative charge, so they must experience an attractive force. Each plate of the capacitor experiences an attractive force due to electric field produced by the other plate. The electric field produced due to positively charged plate would be sigma upon 2 epsilon 0 or Q upon 2 epsilon 0 A. The force experienced by the minus Q charge on the other plate would be Q times C. So that is how we calculate the force. Then force comes out as minus Q times C, that is Q square upon 2 epsilon 0 A. What does the negative sign shows? It shows that force is attractive. Now loss of energy during redistribution of charges. So we have two conductors charged to different potentials. When they are brought in contact with each other, the charge flows from the conductor at higher potential to the one at lower potential till they achieve the same common potential. Redistribution of charge takes place between the conductors. The redistribution of charge is associated with the loss of energy. And remember, charge would be conserved during this process of redistribution. So we have two conductors. Capacitance C1, C2, charges Q1, Q2 with the potentials V1, V2 with the radii R1, R2 named as conductor A and B. So for conductor A, Q1 would be C1, V1 and C1 would be 4 pi epsilon 0 R1. Similarly, Q2 would be C2, V2 and C2 would be given by 4 pi epsilon 0 R2. Now, V is the common potential that would be achieved after redistribution. What happens as per conservation of charge? The total charge before redistribution would be the total charge after redistribution. So Q1 plus Q2 would be equal to Q1 dash plus Q2 dash, and that is Q, the total charge on the system. C1 V1 plus C2 V2 would be C1 V into C2 V, and that is C1 plus C2 into V. So what is the value of common potential? It would be C1 V1 plus C2 V2 is equal upon C1 plus C2 is equal to total charge upon total capacitance. Here C1 is 4 pi epsilon 0 R1 and C2 is 4 pi epsilon 0 R2. So common potential can also be written as R1 V1 plus R2 V2 upon R1 plus R2. So we get the value of common potential that would be acquired by the two conductors after the process of redistribution. Now what are the magnitude of the charges after redistribution? The ratio of the charges Q1 dash upon Q2 dash is given by C1V upon C2V. So Q1 dash would be upon Q2 dash is C1 upon C2 equals R1 upon R2. So after redistribution, the conductor with larger capacitance or size will have larger charge. Using Q2 dash is equal to C2 upon C1 into Q1. What do we get from equation number 2 and use it in equation number 1? So Q is equal to Q1 dash plus Q2 dash. Substitute the value of Q2 dash. You will have Q1 C1 plus C2 upon C1 into Q1 dash. So what is the charge on the first sphere after redistribution? Q1 dash would be C upon C1 plus C2 into Q. Similarly, use the value of Q1 dash from equation number 2 and substitute in equation number 1. What do we get? Q would be equal to C1 upon C2 Q2 dash, and then from here Q2 dash can be calculated as C2 upon C1 plus C2 into Q. What does Q2 represent? Q2 dash, it represents the charge that would be present on the second sphere after redistribution. what is the loss in energy? Before redistribution, the total potential energy is given by Ui is equal to half C1 V1 ka square plus half C2 V2 ka square. Then after redistribution, the total potential energy, that is final energy, would be half C1 V square plus half C2 V square. Substitute the value of V here, so I will get final energy as C1 upon C1 plus C2 upon 2 into C1 V1 plus C2 V2 upon C1 plus C2 ka whole square. So final energy would be equal to C1 square V1 square plus C2 square V2 square plus 2 C1 C2 V1 V2 upon twice C1 plus C2. Now calculate difference in energy by writing UF minus UI and simplify. After simplification, what we obtain? UF minus UI is minus C1 C2 upon twice C1 plus C2 V1 ka square plus V2 ka square minus twice V1 V2, which can be written as V1 minus V2 ka whole square. Now V1 minus V2 would always be positive, this term would always be positive. The negative sign in the equation, what does it show? It shows the loss in energy during the process of redistribution of charge. Where does this energy go? This energy appears in the form of heat in connecting wire or sparking on contact. If V1 is equal to V2, then UF minus UI would be 0. There would be no loss in energy when the two conductors are at the same potential. Why? Because no redistribution of charge would take place. I hope the different concepts of capacitors have been very effectively communicated to you all, and you might have understood them very nicely. Once again, we request, if you understand, then please subscribe the channel, like the videos, and comment in the comment section for further motivation for the videos to come. Here we will provide certain examples which would help you in solving different problems associated with capacitors. First example, it says calculate capacitance of a capacitor with a partially filled dielectric. So we have a partially filled dielectric, we have a dielectric of thickness T, and remember T is less than D. So here let us pick up, consider a parallel plate capacitor with cross-sectional area A and the plate separation D. A dielectric of thickness T is inserted between the plates of the capacitor such that T is less than D. Then potential difference between the plates of the capacitor is given as, here the field would be E0 and here it would be the net field. So let us calculate the potential difference, and the potential difference would be given by E0 into the distance D minus T plus E times T, and what is E? Is equal to E0 by K. So it can be written as E0 D minus T into 1 minus 1 upon K, and writing the value of E as Q upon epsilon 0 A. Taking D common, I get 1 minus T upon D into 1 minus 1 upon K. The capacitance is equal to the ratio Q upon V, so it is given by epsilon 0 A upon D 1 minus T upon D into 1 minus 1 upon K, that is C0 upon 1 minus T by D into 1 minus 1 upon K. So here E0 is the electric field in absence of dielectric, C0 is the capacitance in absence of dielectric, C is the capacitance in presence of dielectric, and electric field in presence of dielectric is given by E. If T becomes equal to D, then what happens? Then T becomes equal to D, this ratio would be equal, and this would be equal to K times C0. C would be now equal to C0 times K, that is capacitance increases. Calculate the capacitance of a capacitor with a partially filled metallic slab. So we have a parallel plate capacitor as usual with the cross-sectional area and plate separation D. A metallic slab of thickness T less than D is kept between the plates. The potential difference is now given by E0 into D minus T. The electric field inside the metal is supposed to be 0. So 0 into T. E0 is Q0 upon epsilon 0 A, and D I take it as common as 1 minus T upon D. The capacitance C is equal to the Q upon V. So I'll get C0 upon 1 minus T upon D. Here we can say capacity increases by introducing a metallic slab, and capacity increases as the thickness of the slab increases. But if T becomes equal to D, then capacity becomes infinite. Such a capacitor will never get charged. So T should always be less than D. Example 3. Determine the equivalent capacitance between the points A and B. These are the 2 points A and B where equivalent capacitance needs to be calculated. Here we are unable to very clearly make out which of the capacitors are in series and parallel. So we adopt something called a junction method. In this, what we do, we mark the junctions as 1, 2 and 3, 4. This is the first junction, the second one, the third one and the fourth one. Draw the equivalent circuit and then find the points of same potential. These are the 3 steps that we normally have to follow. This circuit would represent a Wheatstone bridge. Between 1 and 2 there was a capacitance, between 1 and 3 there was a capacitance, between 2 and 3 there was a capacitance, between 2 and 4 there is a capacitance, and between 3 and 4 is a capacitance. Here this is called P, this is Q, this is R and this is S. If P upon Q is equal to R upon S, then what do we find? The potential of point 2 and potential of point 3 are equal. That means there would be no flow of charge in this branch of the system. This capacitor would be then called as the redundant capacitor or a useless one, which is not charged. So now the equivalent circuit can be written as C and C. We have removed the capacitor here, that is between 2 and 3. So these 2 capacitors now appear to be in series and these 2 capacitors appear to be in series. So equivalent capacitance C by 2 and C by 2 which appear to be in parallel. So the total capacitance between A and B would now be equal to C. A very simple method to handle such complex situations. Another example here. What will happen? Again you have to mark the junctions. So we start with point A. From point 1 we can go to either 3. So one say 3 here. We can go to 2. So one say 2 here. I am utilizing this capacitor and this capacitor. Between 2 and 3 there are 2 capacitors. So between 2 and 3 there are 2 capacitors. These point number 2 and 3 are connected by a wire. That means they are at the same potential. So we mark them at the same potential. From 3 there is a capacitor here which moves to the point B. Now since 2 and 3 are at the same potential, so these 2 capacitors are basically the redundant capacitors. They cannot be charged. So we have these 2 capacitors in parallel here and 1 capacitor in series. So parallel in parallel will give me 2C, another in C in series. So the equivalent capacitance is 2 by 3 of C. Example number 5. Find the effect of inserting a dielectric in a charged capacitor on charge, potential difference, electric field, capacitance, energy stored in following conditions when battery remains connected after introducing the dielectric and battery is removed before introducing the dielectric. So as usual what we say is Q0, V0, E0, C0 and U0 are the charge, potential difference, electric field and the capacitance and the energy stored in absence of dielectric. Now we introduce the dielectric. So battery remains connected even after introduction of dielectric and battery is removed before inserting the dielectric. If the battery remains connected, what is the key point? The potential remains constant because battery will provide the required energy to maintain the potential difference. So V would be equal to V0. As we say, on increase inserting the dielectric, capacitance increases, so C would be K times C0. The initial charge would be given by Q0 C is C0 V0 and final charge Q would be given by CV. So Q upon Q0 would be C upon C0 would be equal to K. So charge on the plate increases, which is the sole cause of increase of capacitance. Initial potential difference and final potential difference. So V0 upon V would be given by E0 upon E and that is 1 because E0 and E are equal. So electric field would remain unchanged since potential remains unchanged. What happens to the energy stored? Let us see. Initial energy stored is U0 equals half C0 V0 square. Final is here CV square. So U upon U0 would be C upon C0 would be K. So energy stored also increases in this configuration. So here what we have done is we have taken into account what happens when the dielectric is inserted and the battery remains connected. Now remove the battery before insertion of the dielectric. If the battery is removed, the potential difference cannot change. So charge on the plates of the capacitor would remain unchanged. So Q would be equal to Q0. Capacitance as usual would increase with the insertion of dielectric. Let us see what happens to charge. So Q0 is C0 V0 and Q would be C times V. Since Q is equal to C0 Q0, so C0 V0 and CV must be equal. So V upon V0 upon V would be equal to C upon C0 would be equal to K. So V would now be equal to V0 by K. That is, potential difference decreases leading to the increase of capacitance. See, in both the cases the physics is totally different. In the first case the increase of charge led to the increase of capacitance, and here the decrease of potential difference would lead to the increase of capacitance. In the two conductor system the physics are totally different. Initial field E0 would be equal to V0 by T and E would be V by D. So E would upon E0 would be V upon V0 would be 1 by K. So E would be E0 upon K. The electric field also reduces following the potential difference. What happens to the energy? Let us see. Initial energy Q0 ka square upon 2C. Final energy Q square upon 2C. So U upon U0 would be C0 upon C would be 1 by K. That is, U would be equal to U0 by K. Here the energy stored also decreases. Question number 6. Prove that charge density is maximum at the pointed end of the conductor. So we have two conductors here, A and B, having the radius R1 and R2, carrying a charge Q1 and Q2. What is the potential of the first one? K Q1 upon R1. Potential of V2, that is the second sphere, K Q2 upon R2. When the two conductors are joined, what will happen? The charge flows to make the potential equal. So let the potentials be made equal. So K Q1 upon R1 would be K Q2 upon R2. K is cancelled here. So Q1 upon Q2 would be R1 upon R2. Now what happens? Charge density sigma 1 would be Q1 upon 4 pi R1 ka square, and sigma 2 would be Q2 upon 4 pi R2 ka square. Sigma 1 upon sigma 2 would be Q1 upon Q2, R2 ka square upon R1 ka square. So R1 by R2 into R2 by R1 ka whole square. So sigma 1 upon sigma 2 would be R2 by R1, or sigma 1 R1 would be sigma 2 R2, or sigma is inversely proportional to R. What happens at the pointed end? R would be minimum, and therefore the charge density would also be maximum. This shows that charge density is maximum at the pointed end of the conductor. Thank you very much. Hope this video makes your concepts of capacitance very nicely understood. Hope capacitance by this video will become easier for you to understand. If you enjoyed the physics of this video, please subscribe the channel, like the video, and we are waiting for your comments in the comment section. Thank you very much. Once again, thank you all.